Imagine a universe at the very beginning of its existence, a cosmos where time has barely begun to tick, and the fabric of space is still settling into its form. The remnants of the Big Bang, an event so powerful that it brought everything we know into being, are still fresh. In this newborn universe, the temperature is blistering, the energy is overwhelming, and matter is only just beginning to clump together to form the first stars and galaxies. Yet, amid this chaotic infancy, something extraordinary and perplexing happens. Less than 1 billion years after the Big Bang, when the universe is still in what we would consider its early youth, supermassive black holes, cosmic giants, millions to billions of times more massive than our sun, are already in place. These ancient entities defy our understanding, challenging the very foundation of what we thought we knew about how the universe evolves. The James Webb Space Telescope, JWST, a marvel of modern engineering and science, has peered deep into the universe's past, revealing these enigmatic objects at the hearts of the first galaxies. These supermassive black holes, or SMBHs, are not figments of theoretical musings. They are very real, and they existed at a time when the universe was only about 500,000 years old. This discovery is not just a curiosity, it's a direct challenge to our understanding of cosmic history. How could such massive structures have formed so quickly when, according to our current models, they should have taken billions of years to reach such colossal sizes? To put this into perspective, let's consider the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A star. It is a behemoth with a mass approximately 4 million times that of our Sun. It took billions of years for Sagittarius A to accumulate this much mass, slowly drawing in surrounding gas, dust, and even stars, all while possibly merging with other black holes along the way. The process of growth for such an entity is slow, methodical, and requires an immense amount of time and material. Yet the supermassive black holes observed by JWST are not only far more massive than Sagittarius A, but they also appear to have reached their immense sizes in a fraction of the time it took for our galaxy's central black hole to develop. This is akin to discovering a towering skyscraper built during the Stone Age, an anachronism that begs for an explanation. The traditional model of black hole formation begins with the death of massive stars. These stars, which are at least several times more massive than our Sun, end their lives in spectacular explosions known as supernovae. When the core of such a star collapses under its own gravity, it can form a black hole. These stellar mass black holes, which typically have masses between a few and several tens of times that of the Sun, can then grow over time by accreting material from their surroundings. This process, known as accretion, is driven by the gravitational pull of the black hole, which draws in gas, dust, and even whole stars. As this material falls into the black hole, it heats up and emits radiation, often making the black hole visible as a bright X-ray or radio source. Over billions of years, these stellar mass black holes can grow into the supermassive black holes we see at the centers of most large galaxies today. But the supermassive black holes discovered by JWST don't fit neatly into this picture. Their immense size, combined with their presence so early in the universe's history, suggests that they somehow bypass the slow and steady process of accretion and growth. Instead, they appear to have emerged fully formed and incredibly massive in a relatively short span of time. This raises a profound question. How did these cosmic giants come into existence so quickly? One possible explanation lies in the first generation of stars, known as population 3 stars. These stars were the first to light up the universe, forming just a few 100 million years after the Big Bang. Unlike the stars we see today, population 3 stars were composed almost entirely of hydrogen and helium, the lightest elements that were formed in the immediate aftermath of the Big Bang. Because they lacked heavier elements, what astronomers call metals, population 3 stars were likely much more massive than most stars we see today, and they burned much hotter and faster. As a result, they would have had relatively short lifespans, ending their lives in massive supernova explosions that could have left behind black holes with masses much greater than those formed by later generations of stars. These early black holes, born from the deaths of the first stars, could have served as the seeds for the supermassive black holes we observe in the early universe. However, even with these massive seeds, It's difficult to explain how they could have grown to billions of solar masses in such a short amount of time. The accretion process, while effective over long periods, simply doesn't work fast enough to account for the rapid growth of these early supermassive black holes. This is where dark matter, one of the most mysterious substances in the universe, might come into play. Dark matter makes up about 85% of the matter in the universe, yet it does not emit, absorb, or reflect light, making it invisible to our telescopes. We know it exists because of its gravitational effects on visible matter, such as stars and galaxies. For decades, scientists have been trying to understand the true nature of dark matter, but it has remained elusive. Now, some astrophysicists, including Professor Alexander Kusenko from UCLA, believe that dark matter might hold the key to explaining the rapid formation of supermassive black holes in the early universe. Kusenko and his colleagues have proposed a theory that involves dark matter halos, vast, invisible clouds of dark matter that envelop galaxies. According to this theory, these halos could have undergone a process known as gravothermal collapse. In a nutshell, this process involves the transfer of heat within the dark matter halo, leading to a situation where the inner regions of the halo collapse to form a black hole. If this process occurred in the early universe, it could have resulted in the rapid formation of supermassive black holes, providing an explanation for the JWST's surprising observations. But even this idea is not without its challenges. For one, the exact mechanisms by which dark matter could drive the formation of supermassive black holes are still not fully understood. Dark matter does not interact with normal matter or itself through anything other than gravity, so how could it cause the collapse of a gas cloud into a black hole? The answer might lie in the possibility that dark matter is not as inert as we once thought. There is a growing body of evidence suggesting that dark matter could decay over time, emitting radiation in the process. This radiation could have a profound impact on the behavior of gas clouds in the early universe, particularly clouds of hydrogen, the most abundant element in the cosmos. Hydrogen in the early universe tended to form molecular hydrogen, where two hydrogen atoms bond together. This molecular hydrogen is crucial because it allows gas clouds to cool and condense, eventually leading to the formation of stars. However, if dark matter decay emitted enough radiation, it could have disrupted this cooling process, preventing the gas clouds from fragmenting into smaller structures. Instead, these gas clouds would have remained large and stable, eventually collapsing under their own gravity to form supermassive black holes. In their research, Kusenko and his team explored the idea that decaying dark matter could emit a specific type of radiation that would have prevented hydrogen gas clouds from cooling and fragmenting in the early universe. This radiation, which could be in the form of photons, might have provided just enough energy to keep the gas clouds from breaking apart, allowing them to collapse directly into black holes. If this process occurred on a large scale, it could explain how supermassive black holes formed so quickly after the Big Bang. Moreover, the team proposed that dark matter could consist of more than one type of particle. Some of these particles could be stable, while others might decay over time, emitting radiation that could influence the formation of structures in the universe. This idea aligns with some of the recent observations made by the New Horizons spacecraft, which detected a faint glow known as the Cosmic Optical Background, COB. The COB is thought to be the sum of all light emitted by stars and galaxies beyond the Milky Way, but there are aspects of it that are not fully explained by current models. Could this mysterious glow be the signature of decaying dark matter? If so, it would provide a crucial clue to understanding the role of dark matter in the early universe and the formation of supermassive black holes. If the theory that dark matter decay contributed to the rapid formation of supermassive black holes is correct, it would represent a major breakthrough in our understanding of both dark matter and the evolution of the universe. However, as with all scientific theories, this idea requires further testing and observation. Future data from JWST and other telescopes could either confirm or refute this theory, shedding light on one of the most perplexing mysteries of the cosmos. While the formation of supermassive black holes in the early universe remains one of the great unanswered questions in astrophysics, the discovery of these objects by JWST has opened up new avenues of research. Whether through the death of the first stars, the influence of dark matter, or some other yet-to-be-discovered mechanism, the existence of these cosmic giants forces us to rethink our understanding of the universe's early history. As we continue to explore the cosmos with increasingly powerful tools, we are likely to uncover even more surprises that challenge our current models and theories. The universe, in all its vastness and complexity, is a place of infinite wonder. Even as we make strides in our understanding, each new discovery seems to raise more questions than it answers. The supermassive black holes of the early universe are a perfect example of this. They are both a puzzle and a promise, a reminder that the cosmos still holds many secrets waiting to be uncovered. With every new observation, every new piece of data, we take another step closer to unraveling the mysteries of the universe. And in doing so, we gain a deeper appreciation for the incredible beauty and complexity of the cosmos.